This is the first part of a 5-part series about Babbage and his engines. Charles Babbage was an English mathematician born in 1791. He spent his life designing engines to automate the production of mathematical tables, such as logarithms, navigation, compound interest, and many others. Now this text you see on the screen, the summary, well, I didn't write this. In fact, nobody wrote this. This text was assembled by artificial intelligence. I logged on to a free account at ChatGPT, put in a phrase or two and some keywords, and it came back with something a bit long-winded. So I typed in make it shorter. And, well, here we are. Now, almost 200 years ago, in 1844 to be precise, this illustration appeared in the English satirical magazine Punch. It was under the heading, The New Patent Novel Writer. The illustration was accompanied by a number of letters, fictional of course. The first was from J. Babbage, not the Charles Babbage, but one J. Babbage. And it read, I have to apologize for some delay in answering your obliging favor, in which you did me the honor of suggesting to me the manufacture of a mechanical lawyer's clerk. After much consideration, I regret that I have found it impossible to produce an article which should be satisfactory to myself and to the profession. I have, however, been completely successful in the production of a new patent mechanical novel writer, adapted to all styles, all subjects, pointed, pathetic, historic, silver fork, and Minerva. I do not hesitate to lay before you a few of the flattering testimonials to its efficacy, which I have already received from those most competent to judge. And among those testimonials was this paragraph. May mention that some days since I placed my hero and heroine, peasants of Normandy, in the surprising adventure department of the engine, set the machinery in motion, and on letting off the steam a few hours after, found the one a duke and the other a sovereign princess, they having become so by the most natural and interesting process in the world. Now, it's quite remarkable, 1840s, and this talk about artificial intelligence, or as they called it in that time, the thinking machine. It was so common, the Punch ran this article. And there are two other remarkable things about this article. The first is this phrase, surprising adventure department of the engine. Well, it only took me about 10 seconds on Google to come up with this advertisement, introducing CoCounsel, the world's first reliable AI legal assistant powered by ChatGPT-4. CoCounsel handles an array of critical tasks for superior work at superhuman speed, giving you more time to better serve your clients and grow your business. The other thing is this illustration. And if we zoom in, we see that the thinking machine not only produced the text of the novel, but it also produced the illustrations. We see on the left the peasants of Normandy being fed in, and they're prancing out as royalty. So what on earth was happening? And what can we attribute this interest to? Well, I think to a large in part, we can lay responsibility on this gentleman. Luigi Menabrea, Italian, came to England and spent time with Charles Babbage and Ada Lovelace. Went back to Italy, eventually became Prime Minister. But he was instrumental in Ada writing the first computer program. And we'll hear about him later because of that. But for now, he published a book about a year before the Punch article appeared. And this book, he has this quotation from Ada Lovelace. The analytical engine might act upon other things besides number. Were objects found whose mutual fundamental relations could be expressed by those of the abstract science of operations, and which should be also susceptible to adaptations to the action of the operating notation and mechanism of the engine. Supposing for instance, that the fundamental relations of pitch sound in the science of harmony and of musical composition was susceptible to such expression and adaptations. The engine might compose elaborate and scientific pieces of music of any degree of complexity or extent. There's two things here. There's an incredible leap from wheels and gears to abstract symbols, not numbers. And there's a whole cult around this statement. I'm sure Ada said it, but I'm not sure she made the abstraction. She definitely made the leap to music. We'll call it steam music, but she definitely invented what we call electronic music, and she deserves full credit for that. Now, Ada Lovelace and Charles Babbage, the daguerreotype and the painting were both done about the same time as Menabre's book appeared, about a year before the Punch article. The daguerreotype on the left of Ada and the painting of Babbage in the National Portrait Gallery. Now, Ada was a gifted mathematician, but she was amateur. And mathematicians, if there is a mathematical gene, she got it from her mother, Isabella Milbank, Queen of Triangles. Ada was known as the enchantress of numbers. But as I said, she's an amateur. She couldn't go to university. She was a woman. And she didn't have the depth and breadth of Babbage's education. Babbage, after all, was a fellow of the Royal Society, founder of the Statistical Society, Lucasian Chair of Mathematics at Cambridge, and was 24 years Ada's senior. Babbage would most certainly have known, and it's very unlikely that Ada would have known, that earlier Leibniz had written, mathematical logic might embody the rules of human reason. 100 years after Leibniz wrote that, Charles Babbage took 10 symbols and put them around wheels with gears, and the underlying gears, cams, etc., implemented the rules of arithmetic. 100 years after that, Alan Turing took 26 symbols, put them around wheels, and the underlying electromechanical mechanisms implemented the rules necessary to break the German Enigma code. 100 years after that, data centers around the world, such as this one, that houses this individual data center, houses over 2 million individual computers. And these computers spend more and more of their time distributing hundreds of thousands, if not millions, of words around their memory. And the underlying logic, the program, understands the statistical relationships between those words. So the programs can produce reasonably literate text like this. Now, Charles's analytical engine, he had decided on a number of different outputs, one of which was what we call a plotter. He didn't build the engine, so this is just a modern diagram, a mock-up. And the plotter would take a mathematical equation, in this case y equals 1 over x, and the engine would move rods around that will push a pen across a piece of paper, thus producing the graph. Well, Babbage realized that to make his engine, he was going to need thousands and thousands of parts, many of which would be duplicates. And he needed a way of doing this. So he came up with the idea of a numerical control machine. He figured if he could push a pen across a piece of paper, he could push a cutter across a piece of metal. So he designed a universal machine tool. Today we call it CNC, computer numerical control. This is a 3-foot by 4-foot engineering drawing, so it looks terrible, having been compressed to the small screen and zoom. Ada was aware of this, and she figured that if a machine could push pens across paper or cutters around metal, it could also operate the valves on an organ. And she well knew about barrel organs. A crank at the top turns a drum with pins, and the pins open valves that let compressed air from the bellows below come out through the organ pipes. And of course, you could only play one tune on it unless you changed the drum. Ada figured that the engine could open and close the valves, so you could play any sort of music you want. So she'd extended Babbage's concept to use levers to drive the valves. And this wasn't a minor step forward. Ada herself was the only one of Babbage's friends and colleagues who realized the implications, and she lifted Leibniz's mathematical logic might employ the rules of human reason from the obscurity of mathematics into the light of, well, music. It changed the world's perception of machines from noisy mechanical contraptions to an entirely new level, hence the thinking machine, as she extended the model of industrial production. Charles Babbage, well, 1791 to 1871. If you watch any video streaming services, Netflix have a series called Bridgerton, and Babbage was born into that series, and he died in another series, the Gilded Age. And in his lifetime, he saw a relatively pristine and certainly simple world. It might have been nasty, brutish and short, but it was an awful lot simpler than what was going to come. In his lifetime, he saw all of that transformed by steam. Farming, land and sea transportation, cottage industries changed into factories, and even in the Brighton Pavilion, the plates were laid out on these long tables. Steam was pumped underneath and through holes in the table to keep the plates warm. Steam was everywhere. But Babbage himself, he's a mathematician. So he saw the world through equations, books of mathematical tables. And he was given the job of checking out some of these tables. One evening, he'd gone out for dinner with his friend from university, John Herschel, the son of the astronomer Herschel. And they were going back to Babbage's house to work on checking some tables used for navigation. And this was a humongously boring and tedious job. It wasn't mathematics. It was just checking, detailed checking of arithmetic. And on the way back to his home, Babbage announced, "I wish to God these calculations had been executed by steam." And this set his life right here and there, because he spent the rest of his time working on engines to automate the routine drudgery of these tables. And the tables in question, you got logarithms, sines, cosines, and tangents for your triangles, squares, square roots, cubes, etc., navigation tables, gunnery tables, compound interest, mortality. It's always at the end of the list, and it says in footnotes for insurance companies, and many more tables, of course. And that's what this is all about. Babbage set out to use steam power to automate the boring bits of doing the simple arithmetic and checking of these tables. I'm not talking about intellectual mathematics, but just the boring bits. And societies grew up, and they had their own number systems, the Egyptians and the Greeks, but none of these systems were very conducive to doing arithmetic. The Greeks didn't bother about that. They just did an end around, and they used geometry. Obviously, Pythagoras is the one we're most familiar with, and Pythagoras' theorem, well, when I look at this, I see 3 squared and 4 squared, as is 3 times 3 and 4 times 4, as in the times tables I was taught as a child. I don't think the Greeks saw it this way. I think they saw it as literally squaring, as in a squared piece of paper drawn out like this. And when we say multiply 3 by 4, I think the Greek idea of multiplication was simply a rectangle. Now, the Greeks knew about powers, and they probably went up above the third power. And years later, mathematicians continued this concept of powers and power series right up until the 18th century and beyond. Bernoulli was very a big contributor to that. And I'm making this sidetrack because it's Bernoulli's equations, like this on the left, that is Ada Lovelace's first computer program was set out to solve. But back to the Greeks. Couple of hundred years before Pythagoras, Hippocrates of Chios was a geometer, not the Hippocrates of the medical oath, but this chap was a geometer, and he came up with what we would call a universal multiplication table. And he drew two lines and used a divider to set off the numbers. I couldn't find any Greek dividers, ancient Greek dividers, that is. I found this pair on the web. But you get the idea. You step the numbers off. The angle between these lines doesn't really matter. If you want to multiply by 3, you draw a line between 1 and 3. And then if you multiply 4 by 3, or if you like, produce a rectangle 4 by 3, you draw a line through 4 parallel to the first line. And where it crosses the second line is the product. It works very well. If you have a fairly large piece of paper, you can get quite good accuracy. You can even do fractions by estimating the position between the numbers. Where it falls down is if you have a large number by which you want to multiply. For example, multiplying by 14. This line here would be the very narrow slope, and the line you draw through the 4 would be such a gentle slope, it would be difficult to tell exactly where it crossed this line. But other than that, it wasn't bad, and it was the only way multiplications could be done until about 1200. The Romans had a go, and they had two arithmetic number systems. Originally, they started off with an additive system with 4 i's for 4 and v and 4 i's for 9. They upgraded that to a version with ix and iv. We're most familiar with this from clocks, of course. But right from the earliest medieval clocks, the clockmakers got it wrong. They used a mixed system. They used 4 i's for 4, and they used ix for 9. Why? I don't know. Possibly it was just a mistake, and everybody copied the mistake. And I support that view because the latest iWatch copied the mistake. But there are some exceptions, clocks that got it right. They're very few and very rare. There's one in a village in Normandy, and there's one that we all know, but we probably didn't recognize it was the exception, and that is Big Ben. And it has the IV and the IX. So how does that help us when we want to do multiplications? 27 times 31. I asked my grandchildren if they could do this in Roman numerals. And I got a resounding, come on, Grandpa. He said, our calculators don't have X's and V's. But that was the way it was. Until about 1000, when word came back from India about a system using zeros, a positional system. But it wasn't well known, and it didn't catch on until around 1200, when Fibonacci, who was the son of a merchant, was brought up in northern Africa, and his tutors were Arabic tutors. And they taught him the system. And when he came back to Italy, he published a book in which he explained the system. It was so obvious and so simple, it really caught on. But it is now possible to multiply 27 by 31. And there is the zero right there. And my granddaughter, we can do this because we learnt the times tables in school. My granddaughters can do it because the calculator has 10 keys on it. But we made a grave mistake in English. We had this ghastly 11 through 19, absolutely nonsensical, but we got it. The Cantonese did a much better job, and possibly in some other languages. The numbers 0 through 10 are, well, just names. and then it goes 10, 1, 10, 2, 10, 3, 10, 4, 2, 10, 2, 10, 1, 2, 10, 2, 3, 10, 3, 10, 1, 3, 10, 2, etc. And purely by coincidence, the words, the pronunciation of the words of 0 through 9 are all single syllables. It so happens that our short-term memory capacity is measured not in terms of words, but in terms of syllables. And so people who can speak Cantonese as a native language particularly can remember more digits than we can in English. And so arithmetic is quite a bit easier for them. But now we have the way of doing these, multiplying these numbers, very useful for numbers like this. But think about Isaac Newton. Poor chap, he was calculating the force between, say, the Earth and the Sun. You've got to multiply the two masses together. Well, those are big numbers, massive numbers. You've got to multiply the distance by itself, divide it into the product of the masses, and then multiply them by the gravitational constant. And if you wanted to do something useful, such as calculating an eclipse, you'd have to use a lot of differences, a lot of digits, to get a high degree of accuracy, which explains why some of his notebook pages look like this. He'd have had to have lived quite a few more years before he'd get any help. And we know that 100 by 1,000 is 100,000. And in Canada, we add the zeros together. In England, you might add the noughts together, but it's the same thing. And if you're a mathematician, you have to be all very fussy and sum the indices. And in all cases, all we've done is converted two big numbers, 100 multiplied by 1,000, into the addition of two small numbers, 2 plus 3. How does that help us with 27 by 31? Well, I took my scientific calculator and I found that 27 was 10 to the power of 1.431, and 31 is 10 to the power of 1.491. So multiplying those two numbers together, all we have to do is add the indices, and then you get 10 to the power 2.922. I use my calculator again to go backwards and find the answer of 837. Now, that's of obviously no benefit when you're multiplying 27 by 31. And you can't calculate these powers here without a calculator. Well, you can actually. What you need is a book. And if you could go to the book and you look up 27 and it says it's 1.431, and you look up 31 in the book and it says it's 1.491, then you can add those two numbers together, which is easy enough to do. And then you can look up 2.922 in the back of the book and get the answer of 837. I'm sure most of you have recognized that what we've done is use logarithms. And tables of logarithms look a bit like this. And of course, it begs the question, where did logarithms come from? Well, we had to wait till John Napier. And in around 1600, he produced this book, 1614, in fact. He was a Scottish mathematician, and the book contained logarithms, but he worked at it before Newton, so he didn't know about calculus. And so he didn't do a very good job on it. The tables were incomplete and contained a lot of errors because he had to use a very complicated process using approximation, successive approximations. But we can't give him credit for his effort, and we can definitely give it credit because the numbers he produced in his tables were used to build the first slide rule. We had to wait for Leonhard Euler to come along, the Swiss mathematician, who came up with an equation for logarithms. Now, I did threaten in the summary of these talks I was going to do some arithmetic, and here it is. We're going to calculate the logarithm of 3. And bear with me, because it isn't that hard. You stick 3 in this equation, and there's two things about the answer. First of all, it goes on forever. And secondly, and more importantly, the numbers at the bottom get large very quickly. You divide 1 by a large number, you get a small number. you divide 1 by a very large number, you get a very small answer. So I calculated the first numbers from this equation here. And the logarithm of 3 is, of course, the sum of all these numbers. But when you get down to here, we don't have to worry about the rest. All these numbers down here are so small, for everyday use, they're meaningless. If we were doing some calculations to make something, then you can't measure anything smaller than 1/1000th of an inch. And certainly in Victorian times, you couldn't make anything with any greater precision. So we can forget all these numbers. The sum of all these numbers to infinity don't add up to anything worth worrying about. So we can come up with a table of logarithms to 4 digits of accuracy, 1, 2, 3, 4, by simply using the first 4 terms from Euler's equation. Now, it's still pretty intimidating, because if you wanted to do 4 digits of precision, you'd have to do 9,999 of these, this equation. Of course, the first term is easy, but you've still got 3 terms that are difficult to do. So it's pretty intimidating. But we get some help, because first of all, I used the first 4 terms from Euler's equation to run a spreadsheet to get the logarithms of 3.000 through to 3.008. But it's not really much help. To get some real help, we had to wait till the English mathematician Brooke Taylor came along. And Brooke Taylor said, take the differences. But I'm going to switch from logarithms to a much easier polynomial. And a polynomial is just an equation that has squares and cubes and such like. And this is an easy one, n squared, because we can do it on our head, 1, 4, 9, 16, etc. Brooke Taylor said, take the differences. Okay, 4 minus 1, 9 minus 4, gives us 3, 5, and 7. So, big deal. Well, he said, take the differences. Oh, they're all the same. So we can calculate the square of 5 by adding up the 3 numbers above, 25. Then we can take 2 differences. And really, we don't have to do the second difference because we know what it is. And then we can carry on. The square of 6 is the sum of those numbers, 36. And take the differences, add them together, and get 49. And we can keep going. We can go as long as we want. It's a bit tedious to do so, so I used a spreadsheet. And I ran the spreadsheet, just taking the sums and differences, and I went all the way up to 1465. So if we wanted to calculate the square of 1466, it's just the sum of those numbers, and that's correct. And we can take the differences and add them together, and we get the square of 1467. All very good. Well, going back to logarithms, we can do exactly the same thing. We can take the differences, we can take the second differences, and they're all the same. Now, getting them all the same in the second column is just a coincidence. I chose logarithms, I chose 4 digits, so that this would work because I wanted to make it simple. If we wanted 6 digits of precision, or we did some other equation, for example, compound interest, we might have to go to more columns, might have to go to more differences. But as I said, I wanted to keep it simple. So we can calculate the logarithm of 3.009 by adding these 3 numbers up here together. And then we can take 2 more differences, or actually 1 difference, because the difference number 2 is always the same. I calculate the logarithm of 3.010. Now that's all very well and good. And I was a bit worried at this point that somebody might have grabbed a calculator and looked up the logarithm of 3. And they're going to be immediately writing me an email to complain that I got it completely wrong. And the reason for that is that Euler's formula computes what's called natural logarithms, which is to base e. For normal arithmetic, we want common logarithms to base 10. And on most calculators, log is a common logarithm, and lg is the natural logarithm. So if you just go to your calculator and look up log of 3, you get a different answer. If you use lg to look up the logarithm of 3, you'll get an almost correct answer. Well, you will get a correct answer, but you'll find a small error in my formula. And here it is. This 3.002 was an error down here, 2788, 2775. Well, the reason it's there is that we only used 4 terms from Euler's equation. So we're not quite correct. When we get down into the umpteenth decimal place, we're slightly out. And as we go through the successive additions and subtractions, this error grows. And at some point, it'll get large enough that it will affect the result. But we said we only wanted 4 digits of precision. So we don't care about the errors down here. It's perfectly all right. But it does accumulate, and it will bias the answer. And that's why you'll see logarithms printed in books like this for arguments 2 to 1,200. I think this was a book of 9-digit logarithms, and the authors would have made the tables of differences starting at a particular point and with enough columns that their accuracy would survive between 2 and 1,200, at which point they'd have to start all over again with a different set of numbers from a reworking of the formula. So we now have a way of calculating logarithms with a repetitively boring way of doing it, but not difficult. So who's going to take advantage of it and do something with it? Well, surprise, it's Napoleon. Here he is charging across the Alps to rescue his army. And Napoleon was really into order. Meters, grams, a 10-hour day, 100 minutes in an hour, and 100 seconds in a minute. He was also concerned about his image. After all, he was a leader. An image is very important. And at that time, the French used feet in inches. But the French foot was longer than the English foot, so he was only 5'7". But after using meters and then doing the correction to the English foot, he came out at 5'9", which wasn't a bad height at that time and certainly helped his image. So how did he go about these tables? Well, he hired a mathematician from Paris, de Prony, who in turn went out and set up 2 groups. He had about a dozen mathematicians. Their job was to select the formula they were going to use for a particular table. Logarithms, of course, would have been Euler's equation. And these mathematicians computed the starting values and pivot points. I'll come back to pivot points later. He also hired between 80 and 100 computers. At that time, a computer was a term given to a person whose job it was to, well, compute, add and subtract in this case. Excuse me. What he did was have his mathematicians calculate the starting entries in the table, in this case, common logarithms. Once they got starting points, they could set up these tables of differences, and then the computers could carry on. But they might make a mistake. And if they make a mistake, every number from there on will be wrong. So he had his mathematicians calculate these pivot points here and here as an example. So if the computer made a problem here, everything down here would be wrong, and it wouldn't agree with the results at the pivot point. So we go back, find the problem, fix it before carrying on. De Prony very quickly realized that when problems occurred, they were mostly a result of the mathematicians, not of the computers. So he sent the mathematicians, well, when he wanted to calculate a pivot point, he gave the problem to 2 mathematicians, send them off into separate rooms, and when they agreed on their answer, they come back and check on the tables when the computers had got up to that point. In the last decade of the century, They produced tables of logarithms, natural and common, sines, cosines and tangents, square roots, cubes, etc., navigation, gunnery, compound interest, mortality. In fact, more than 5 million numbers were produced. And this was a vast business with values calculated to between 14 and 29 decimal places. Each copy consisted of 18 folio volumes together with another volume of mathematical procedures. It was absolutely a horrendous job. Nothing had been accomplished like that before. And the cost, of course, was quite phenomenal. But Giuliani kept his costs down because he hired hairdressers for his calculators, the computers, I mean. The hairdressers knew how to add up numbers to figure out the bill and knew how to subtract because they had to give change. And hairdressers came cheap. They were the first profession to be made obsolete by automation, their clients having been taken off to the guillotine. So we have tables, and we know how to make the tables. Of course, we've still got some errors in them, it's inevitable, but we know how to do it. And that's exactly what Charles Babbage attempted to do with his first engine, the difference engine. Here it is at the Science Museum, and we'll talk about it in the second talk, and we're going to have a engine worked in some detail. The first is this phrase, surprising adventure department of the engine. Even in the 1840s, the Punch writers realized that artificial intelligence would be specialized. It took me all of 10 seconds to find this advertisement by Google. Introducing CoCounsel, the first reliable AI legal assistant powered by ChatGPT-4. Let CoCounsel handle an array of critical tasks for superior work at superhuman speed, giving you more time to better serve your clients and grow your business. And this illustration, I'll zoom in, we can see that the thinking machine not only wrote the text of the novel, but it produced the illustrations. On the left, we see the peasants of Normandy, and on the right, they're prancing out as royalty. So what on earth is going on? And who we could attribute for starting this interest? And I think we can mainly attribute it to this gentleman, Luigi Menabrea, Italian, came to England and spent time with Ada Lovelace and Charles Babbage. He went back to Italy and eventually became Prime Minister. And we're going to hear from him later because he was instrumental in Ada Lovelace writing the first computer program. But for now, we're interested in a book he published about a year before the Punch article. And it contained this rather lengthy quotation attributed to Ada Lovelace. The analytical engine might act upon things other than numbers. Were objects found whose mutual fundamental relations could be expressed by those of the abstract science of operations, and which should be also susceptible of adaptations to the action of the operating notation and mechanism of the engine. Supposing, for instance, that the fundamental relations of pitched sounds in the science of harmony and of musical composition were susceptible of such expressions and adaptations. The engine might compose elaborate and scientific pieces of music of any degree of complexity or extent. Now, this is an incredible leap from wheels and gears to processing abstract symbols, not numbers. There's a whole cult grown up around this, and I'm sure Ada actually said it, but I'm not sure she made the original abstraction. She certainly made the leap to music, and we can certainly credit her with the invention of electronic music, or perhaps we should call it steam music. This daguerreotype of Ada Lovelace and the painting of Charles Babbage in the National Portrait Gallery were made about a year before the Punch article appeared, about the same time as Menabre's book was published. Now, Ada was a gifted amateur mathematician, and as a mathematical gene, she inherited it from her mother, Isabella Milbank, known as the Queen of Triangles. Ada herself was known as the Enchantress of Numbers. She was an amateur, and at that time, women couldn't go to university. She was home tutored. So she didn't have the depth and breadth of Babbage's education. After all, Babbage was a fellow of the Royal Society. He was a founder of the Statistical Society, held the Lucasian Chair of Mathematics at Cambridge, and he was 24 years Ada's senior. Now, earlier, Babbage would have known, but it's unlikely Ada would have done, that Leibniz had written, mathematical logic might embody the rules of human reason. 100 years after he wrote that, Charles Babbage put 10 symbols around wheels, and the underlying mechanism, gears and rods and such, implemented the rules of arithmetic. 100 years after that, Alan Turing put 26 figures around wheels, and the underlying electromechanical mechanism implemented the rules necessary to break the German Enigma code. 100 years after that, more and more data centers around the world, such as this one, that houses in excess of 2 million individual computers, distribute hundreds of thousands, possibly even a million, symbols around their memory. The symbols represent English words. And the underlying program, the underlying logic, understands the statistical relationship between these words, and therefore can produce quite literate text. Ada Lovelace was aware of the work that Babbage was doing. She was aware of his analytical engine, shown in his plan view here. The engine was designed with several outputs, one of which was a plotter. And he could plot, if it had been built, it would have plotted graphs like this, y equals 1 over x. Babbage had designed a mechanism that had rods that would move a pen around on a piece of paper. Babbage also knew he would have to manufacture thousands of parts for this machine, and he would require hundreds of multiples of individual parts, a manufacturing process completely unheard of at that time. So he figured if he could push pens over pieces of paper, he could push a cutter across a piece of metal. So he designed what he called a universal machine tool. This is a 3-foot by 4-foot engineering drawing that Babbage produced, and unfortunately you can't see it very well because of the compression. But he had designed, in fact, computer numerical control, CNC machines, which are used extensively today in industry. Ada was certainly aware of this, and she figured that if Babbage's machine could push a pen across a piece of paper or move a cutter across a piece of metal, then he could certainly open and close the valves in the barrel organ. The barrel organ is quite simple. There's a bellows at the bottom, the pipe brings air up to a rotating drum with pegs. And as it rotates, with the crank in the front top there, as it rotates, the drum opens and closes valves that feed the air up to the organ pipes. So Ada figured that the analytical engine could operate the valves to play the organ. Thus, it could play any tune that was programmed in and didn't have to rely upon changing the barrel. And this leap was not a minor thing. It was an incredible step. And Ada was the only one of Babbage's friends and colleagues who realized the implications, and she lifted Leibniz's mathematical logic might employ the rules of human reason from the obscurity of mathematics into the light of, well, music. It changed the world's perception of machines from noisy mechanical contraptions to an entirely new level, hence the thinking machine. It extended the model of industrial production from things to thoughts. Charles Babbage himself, 1791 to 1871. If you watch streaming services, he was born into a Netflix series called Bridgerton, and he died in another series called The Gilded Age. His youth was, by modern standards, quite simple. It was certainly nasty, brutish, and short, but we might even think of it somewhat idyllic. He saw all of that change. He saw steam being used on the farm, for land and sea transportation. Cottage industries transferred to massive factories, and even steam in the Royal Pavilion at Brighton. The steam was piped under his long tables that had holes in. Plates were laid out over the holes, and the steam kept the plates warm. It was still nasty, brutish, and short, but it was now incredibly complex. Now, Babbage was a mathematician. He saw the world through the eyes of equations and mathematical tables. And he and a good friend, John Herschel, a son of the great Herschel, astronomer, they were out having dinner one day, and they had been assigned the task of checking some navigation tables, which would be incredibly tedious and boring work. And on the way back to Babbage's house to do this, Babbage exclaimed, "I wish to God these calculations had been executed by steam." And these tables include logarithms, sines, cosines, and tangents for triangular calculations, squares, square roots, cubes, etc., navigation tables, gunnery tables, compound interest, and at the end of the list, mortality, with a footnote for insurance companies, and other tables as well. Now, the point is, producing these tables was extremely tedious and difficult work. Well, not mathematically difficult, but tedious work. And Babbage had seen steam being used for replacing manual labor. So he was wondering if it could be used to replace these mental labor, the boring methodical stuff, not mathematics, but the boring stuff of adding and subtracting. And this is what it's all about. It's about transferring from mental labor to steam-powered labor. Now, from the earliest time, civilizations had number systems, and some of them tried more than one system. The Greeks went through a couple, but none of them were conducive to doing arithmetic. The Greeks decided to do an end around. They used geometry. Pythagoras is the best known, and of course, Pythagoras' theorem. When I look at 3 squared and 4 squared, I think of the times tables. I think of 3 times 3 and 4 times 4. I don't think the Greeks did that. I think the Greeks thought that 3 times 3 was really literally 3 squared, as in the drawing, and 4 would be 4 squared. And multiplying 3 by 4 wouldn't be multiplication, it would be making up a rectangle with a side of 3 and a side of 4, containing 12 smaller squares. The Greeks were certainly aware of powers, and later on, in the 17th and 18th century, mathematicians extended this concept of powers to this sort of series. And Bernoulli was one of the mathematicians that was key to this. This digression is important because Ada Lovelace's first program solved these types of equations. Back to the Greeks, a couple of hundred years before Pythagoras, Hippocrates of Chios, and this is not the chap who was the medical fellow. This guy did geometry, and he came up with what we would call a universal multiplication table. He drew two lines, the angle doesn't really matter, and spaced off a number line on both sides using dividers. I couldn't find a picture of any ancient Greek dividers, but these were in the Smithsonian, so they'll have to do. So what he did, if you wanted to multiply by 3, you draw a line between 1 and 3 and extend it up. If you wanted to multiply 4 by 3, then you draw a parallel line through the number 4 at the bottom, and it crosses the top line at 12, which gives you the rectangle of 3 times 4. It's a perfectly good way of doing it, and if you use a good large enough piece of paper, it can be fairly accurate. You can estimate fractions by drawing your line between the numbers. And that was the only way of doing multiplication up until about 1200. It falls down if you multiply by a very large number. For example, if you multiply by 14, then that first line between 1 and 3, has to go up to 14, 1 to 14. So very shallow angle. So the parallel line through 4, it'd be quite difficult to tell exactly where it crosses the left-hand number line. But for similar numbers, it was okay. The Romans came along. They had two number systems. They started with an additive system, 4 i's for 4, and v and 4 i's for 9. Later, they improved it to a subtractive system, where iv became 4 and ix became 9. We're most familiar with the Roman system, of course, from clocks. And right from the earliest medieval clock, they made a mistake. They used a mixture of the units. They used 4 i's for 4 and ix for 9. Why? I don't know. I suspect the first clockmaker made a mistake and everybody copied. And I support that because the latest Apple iWatch reproduces the same mistake. But there are some clocks that got it right. Very few, very rare. There's a village clock in Normandy, and there's one clock that anybody who's been to London will have seen, and that's Big Ben, IV and IX. Well, how does the Roman system help us? I asked my granddaughters to multiply 27 by 31 in Roman numerals. I got a resounding, "Don't be silly, Grandpa, our calculators don't have X's and V's." I was quite sympathetic to them. It wasn't until about 1000, year 1000, thereabouts, that word started to come back from India about a new method of doing arithmetic using 0, a positional system. It didn't become popular until around 1200, when Fibonacci, a son of a merchant, had been brought up in North Africa, and he'd been studying mathematics from Islamic teachers. So he published a book that contained the system with zeros. And because he'd learnt it from Arabs, he called it the Arabic system, which I think is rather unfortunate because the people that really designed it were the Indians, and they don't get credit. But at last, for the first time, we can multiply 27 by 31, the way I was taught in school in the 1950s. And here you can see the zero in use. My grandchildren, of course, can do this because their calculators have 10 buttons on them. Now, the zero was at first thought to be just a placeholder. It was only later that somebody pointed out that it was average of -1 and +1. So it became a number in its own right. And somebody else pointed out that the average of -2 and +2 was also 0, and it had to be twice the average of -1 and +1. And that is why every number multiplied by 0 is, well, 0. The English made a mistake. They chose this abomination of 11 through 19. No logical sense at all. In Cantonese, and possibly other languages, they got it right. The numbers 0 through 10 are then followed with 10-1, 10-2, 10-3, etc. 2-10, 2-10-1, 2-10-2, 3-10, 3-10-1, 3-10-2. Very simple, very logical, and even better, and it's probably by chance, the pronunciation of the words 0 through 10 are all single syllables. It happens that our short-term memory capacity is measured not in words, but in syllables. So a Cantonese speaker will find it a lot easier to remember long numbers than in English and many other languages. So here we have the way of doing the multiplication, and it works very well for fairly small numbers. But think for a moment of Isaac Newton. Isaac Newton was calculating the force between bodies, for example, between the sun and the earth. So you have two very massive numbers here, which are multiplied together. And the distance is a very big number as well. So you have to multiply it by itself to get the distance squared. You have to do the division, and then you have to multiply by the gravitational constant g, and that will give you the force. Now, if you wanted to do something useful, such as calculating the next eclipse, you would have to use quite a few digits. And this arithmetic would be very difficult, which is why some of his notebook pages look like this. He would have had to have waited quite a few years after his death to find an easier way of doing it. Now, we know that if you multiply 100 by 1,000, you just add together the zeros or the noughts, and depending where you live, and you get the right answer. If you're a mathematician, you have to be very fussy and sum the indices. But in both cases, you get the same answer. And what you've done is converted two large numbers, 100 and 1,000. You converted the multiplication into the addition of two small numbers, 2 and 3. So how does that help us with 27 times 31? Well, these indices, 2 and 3, don't have to be whole numbers. So I used my scientific calculator, and I found out that 27 was 10 to the power 1.431, and 31 was 10 to the power 1.491. So multiplying 27 by 31, we can add these two indices together and get 10 to the power 2.922. Using my calculator again, I found out that it was 837, which is the correct answer. Now, that doesn't help us very much with 27 times 31, particularly if we didn't have a calculator. But if we had a book, and if we could go to the book and we look up 27 and find it was 1.431. And we could look up 31 and find 1.491. And we could go to the back of the book and look up 2.922 and get the answer of 837. Then this will certainly help Isaac Newton. And some of you have probably recognized by now that this book is a book of logarithms. Which begs the question, of course, how do you make a book of logarithms? The first person to attempt this was John Napier. He published in 1614 a book of logarithms. He lived before Newton, so he didn't know the calculus. He used a rather complicated method of approximations, which meant his tables were incomplete and had quite a few errors. So we'll give him 10 for effort, but not so much for the results. But his tables were used for building the first slide rule, which was an incredibly useful device for doing arithmetic. We had to wait a while until Leonhard Euler came along, Swiss mathematician, and he came up with a formula for calculating logarithms. Now, in this summary at the beginning, I threatened the use of some arithmetic, and here it is. We're going to calculate the logarithm of 3, and please bear with me because it isn't that complicated. So you stick 3 in where it says y here, and expand it, and you get this long series. And this series up here goes on forever. But the nice thing is the numbers, 1 divided by the number 3 times 8, is quite a small answer. If you divide 1 by a much, much larger number, you get a much, much smaller answer. So the numbers at the bottom here get larger, larger, larger very quickly, which means the divisions are going to provide smaller and smaller results. So I ran a spreadsheet and I calculated the first 8 terms of the Euler's equation. We've only got 4 terms shown on the left, but here are the 8 terms. And the logarithm of 3 is the sum of all these numbers because it's the sum of these terms. But we don't have to worry about going on forever. We can cut the thing off right here. If we were calculating a dimension to make something, then we don't have to worry about anything under this line. In fact, if you add all of these together, excuse me, all the way up to infinity, it's insignificant. After all, we can't measure anything this small, 0.0004 of an inch, without modern equipment, that is. So we can treat the logarithm of 3 as just the sum of these 4 numbers here, which is the sum of these terms here. And if we wanted to calculate all the logarithms of all the 4-digit numbers, we'd have to do this type of calculation 9,999 times, which would be a bit tedious. Mind you, doing the first term in the equation isn't too difficult, but it will still be a lot of work. And nevertheless, I used a spreadsheet and I calculated the first 4 terms of the 9 logarithms between 3.000 and 3.008. So what? Well, we had to wait a little bit longer, and then Brooke Taylor came along. And Brooke Taylor was an English mathematician. And Brooke Taylor said of this problem, take the differences. Well, what does that mean? Well, I'm going to leave logarithms for a bit and go to something really simple. Euler's equation has squares and cubes in it, and it's what we call a polynomial. And here's a much simpler polynomial, n squared. And I'm using this because we can do it in our heads. N and n squared, well, it's obvious. So Brooke Taylor said, take the differences. So let's do that. 4 minus 1, 9 minus 4. And the result is 3, 5, and 7. So what? Well, Brooke said, take the differences. So let's take the differences. And surprise, they're all the same. Now, it happens that if we wanted to calculate the next number in the series 5, it's the sum of the numbers above, 16 plus 7 plus 2, which is 25. Now, if we do two differences, 25 minus 16 is 9, and 9 minus 7 is 2, and write them in, then the square of 6 is the sum of those three numbers above. And there it is. And we can go on like that, calculate the two differences. Well, actually, only the first difference, because the 2 is always the same, so we don't have to calculate that again. And then we can add up the three numbers above, the 36, 11, and 2, and get the square, which is 49. And we can do that as long as we want, except it gets a bit tedious. So I used a spreadsheet, and it's just summing and subtracting, adding and subtracting. And I let it run up to 1,466. And yes, the second number is still 2, and I did actually do the subtractions in the spreadsheet. So if we want to find the square of 1,466, all we have to do is add those three numbers together, and we get the square. And we can do it again and get the square of 1,467. There it is. So any polynomial, by doing the differences, and it's called the method of finite differences, we can run this as long as we want and produce the results of any polynomial that we want. And here we'll go back to the logarithms. And that worked for n squared, so let's try it here. Take the differences. Take the differences of the differences. Now we can calculate the logarithm of 3.009. Calculate two differences, and we can calculate the next logarithm. Now the fact that the column 2, difference 2, is always the same, both for this polynomial and for x squared, is a coincidence because we chose to use 4 digits of accuracy. And I chose logarithms and n squared, so it will come out as the same in the second difference, to make it simple, because I think I've confused you enough already. But if you chose a different calculation, for example, compound interest, you may well need more differences. And if you choose a higher degree of precision, maybe 6 digits instead of 4 digits, you would definitely need more difference columns. And I'm going to make a slight digression here, because somebody might have grabbed a calculator and looked up the logarithm of 3 and be concerned that I got completely the wrong answer. The reason is that Euler's equations calculates logarithms called natural logarithms, and they are of a base e, which is a mathematical constant. If we want to calculate common logarithms of base 10, and those are the ones we'd need for doing decimal arithmetic, there's an extra step, and I left the step out again to keep things simple. But if you then grabbed your calculator and looked up LG, which gives you natural logarithms, as distinct from LOG, which will give you common logarithms, at least on most calculators. If you'd used LG to look up the logarithm of 3, you'd still find that I had an error. Now it happens that it's a small error. And since we're only interested in 4 digits of accuracy, that small error doesn't matter, because the 1.099 is perfectly correct, and the error occurs down 3 digits later. So we can forget it. But if we wanted to calculate all the 4 digit numbers, logarithms, we'd have to keep an eye out, because that error through the successive additions and subtractions starts to accumulate. And the error is only there because we use the first 4 terms from Euler's equations. If we use 6 terms from the equation, We need more difference columns, and this error would appear further down in the results. So we could produce logarithms of larger numbers. But we do have to keep an eye on it, because at some point, the error will encroach into the number of digits in which we're interested. This is why, when you look at old books containing logarithms, you'll see they'll say things like this for arguments 2 to 1,200. I think this might have been a book of 9-digit logarithms. And the base they chose, in other words, the number of terms from Euler's equation, was such that it would produce numbers in this range. By the time they got up to 1,200, the successive adding and subtracting wouldn't work anymore because this error will have encroached in the numbers we're interested in. So we'd have to start again. So we have a way of calculating mathematical formulae by using the method of finite differences. So who's going to take advantage of this and produce tables this way? Well, surprise, it's Napoleon, leaping across the Alps to rescue his army. And he was very much into ordering things: meters, grams, 10 hour a day, 100 minutes in an hour, 100 seconds in a minute. And he was interested in producing all these tables because it would be beneficial to his army. He was also concerned about his image. And at that time, the French used feet and inches, but the foot they used was a little bit longer than the foot they used in England. So in French units, his height was 5'7". When his height was measured in meters, and you used the correct conversion from meters to the English foot, he had suddenly grown to be 5'9". So he was keen on this, and in 1790, he went out and hired a French mathematician, Gaspard de Prunier. And in the last decade of the century, de Prunier went out and hired about a dozen mathematicians, and their job was to select the formula they would use for a particular mathematical table. And the mathematicians would compute the starting values and also pivot points, and I'll come back to those later. He also hired between 80 and 100 computers. At the time, the word computer was applied to an individual whose job it was to compute, in this case, add and subtract. So as an example of the common logarithms, the mathematicians would choose the equation. The mathematicians would work out the first few entries in the table, and then the computers would carry on doing adding and subtracting. But he realized that if the computer made a mistake, every number from there on in would be in error. So he had his mathematicians work ahead of the computers and calculate these pivot points. And I chose a couple of places there that are convenient. When the computers got down to that point, they could compare their answers, and if they agreed, they'd carry on. If they didn't agree, then they'd backtrack and fix the error. It didn't take de Prunier very long to realize that most of the errors were done by the mathematicians. So he gave the problem of a pivot point to 2 mathematicians, sent them into separate rooms, and only when they agreed on their answer would they write up the pivot point and wait until the computers got there. And between 1790 and 1799, these teams did an incredible job. They produced natural logarithms and common logarithms, sines, cosines, tangents, square roots, cube roots, and other similar tables, navigation tables, gunnery tables, compound interest, mortality for the insurance companies. They produced more than 5 million numbers. This was an incredible piece of work. It was vast, with values calculated to between 14 and 29 decimal places. Each copy consisted of 18 folio volumes, together with another volume of mathematical procedures. That means that those people were producing somewhere around 50 million digits. And it was incredibly expensive. And to keep costs down, Dupronnier hired French hairdressers. Now, they knew how to add numbers together because they had to sum up the services they provided, and they knew how to do subtraction because they had to give change. And they came cheap because French hairdressers were the first profession to be made obsolete by automation. Their clientele were taken to the guillotine. So we have our way of calculating logarithms and any other mathematical table that's based on polynomials. And Babbage's first engine, the difference engine, wasn't built in his lifetime. He started it, but he ran out of money. So it was built in the 1980s, and here it is. And it was specifically designed as a calculator to do the successive additions and subtractions. So you can see in these columns here, the columns are the columns for the differences. And we're going to talk about this next week.